Start, I guess. So hi, everyone. Good morning. Today we have a Tuesday talk on Monday by Elon. So, it's one of the things we're happy to be at IIS for, where we can have people from different areas speak to different seminars. Analog coding, list decoding, maybe we know, bandwidth, mean dimension, I don't know that many of us know. So I hope Elon is patient to our questions, and please ask as many questions as you can to make things clear.
And I'll add, in the abstract, there was another important term. Right. Distortion. Basically, my aim is fairly modest, and I'm not sure if I'll be able to pull it through. My aim is just to go carefully and explain these words, and hopefully as I explain these words, I will also explain the relationship between them. And I'm going to start from the end and go to the top, and let's talk about mean dimension. But actually, if I really want to start with the end, let's talk about dimension. It's a standard thing, but I'll talk about dimension. So I have X. I'm going to do things simple. So X will be compact, nice space. Nice, meterizable, but I am not really sure I want to put a metric on it at the moment.
Do we have something like a concrete example we can keep in mind to make things?
RD.
RD. Okay.
RD. That's concrete enough.
That's very good.
Yeah. And then, okay, RD is not compact, so it's a cube.
Okay.
In definition, the dimension of X is, well, this is the covering definition of topological dimension if for any open cover, because we are careful sort of to talk about compact spaces, we can take a finite open cover. So we can find a subcover. With multiplicity. So what we have multiplicity, there's no point belongs to more than d+1 sets. Okay, that's sort of definition of dimension. And it's the first time you see it, you sort of wonder how is that related to dimension. So let me give a small variant of it, which is easily to which is easy. Okay, now I'm running into a real problem. I want to denote the dimension and the metric by D. And okay, I've confused myself if I don't do it, and I'm pretty sure it won't cause a confusion. So there'll be two little d's. One of them is going to be the metric, one of them is going to be dimension. And when confused, ask. So there's a completely equivalent. But I sort of started with this definition because A, it's a standard definition, and B, because you see it doesn't depend on the metric. So now take D to be a metric on X. And we say that the dimension of X is most D if for any epsilon positive, we can find a D or smaller dimensional simplicial complex modeling it up to accuracy So this maybe can be interpreted in several ways. Here are the concretes. So this is sort of, if you want more formal, if you want a more formal definition, for every there is a simplicial complex, geometric simplicial complex K, and a continuous map phi from a space to, okay, a simplicial complex is sort of all sorts of triangles and tetrahedrons and points and whatever glued together. Sort of has all sorts of combinatorial information. If I forget the combinatorial information, just consider the points with obvious topology, I denote it by absolute values.
Maybe say you can think of the point as placed in R and
No, this I don't know.
you don't want.
No. But okay, that's, I think, a graph is something I'm allowed to talk, even if it's not planned.
No, but when you put these two lines on the graph, it's not very familiar.
Yeah, okay, it's just you have these triangles connected together, and it has, each triangle has an obvious, it has an obvious topology, and I just look at the points and I forget about the combinatorial structure. I mean, I tried to check what is the standard terminology for that, and it's not, I hope I got it right. You know.
What's the end of the definition? What is the end of the definition?
Yeah, so there's a continuous map. So that for any point P in the simplicial complex, diameter of the inverse of the point is at most epsilon. Okay, it's a reasonable definition, and at least to me,
So the map is the map is
It's not onto, but it's like.
no, it's not injected, but it's sort of,
of subject.
it's not that to be subject. But it's big enough that you could distinguish between points that are epsilon apart. That's all I'm saying. Maybe the whole, maybe my space is a point and I map everything to a point. I'm happy about that.
No, so yeah.
I'm not assuming subjective, not assuming. You're missing detail of the definition of dimension, so I think you're in good shape. And I'm being quizzed about it, but that's good. I like it. So now, this actually makes sense even for an infinite dimensional. Either this notion makes sense even if my space for definition Wi dim. Epsilon is exactly the minimal dimension of a simplicial complex.
Wait, what does it say there? WI?
Wi dim of x d epsilon. The amount of dimension captured, this is the metric. The amount of dimension captured up to resolution epsilon. If I take off my glasses, I can now distinguish things which are roughly, I don't know, 10 centimeters by 10 centimeters apart. How much dimension do I see without my glasses?
And what is the WI stand for?
I don't know, but Kromov wrote it, so it's okay.
Oh, no. So the D here is the metric?
D here is a metric. And epsilon is accuracy.
You don't want
and
it
X
to be
is the
too
space.
simple, you know?
No, okay, right, I'll already.
Unfortunately, we're going to play with that. That's what I do. It's not, I mean, if somebody gives you a JPEG, okay, and you want to encode it, is it obvious to you what metric to use, how good you're encoding it? No. So it's not obvious what metric to use, not to you, not to me.
Sure.
The minimal dimension of simplicial complex epsilon modeling A. Okay, in this set. And then, of course, so dimension of my space is at most t if the limit epsilon goes to 0, wi dim. This is obviously going to be monotone increasing. Is the okay, so that's just saying again what I said. Now, example. I'm going to take an example. And I promise to you I'm not going to do anything complicated. So here's an example. That's a cube. And I need to define a metric. So dxy is going to be x minus y infinity. No, that's the most convenient for me here. And then wi dim x with respect to this metric, and epsilon is going to be equal to d for any epsilon bigger than 0, less than 1. Obviously, you could triangulate the cube, so it's obviously just the identity map models x up to resolution epsilon. I'm going to be a bit sloppy about distinguishing between simplicial complex and cell complex. If I multiply two simplicial complexes, it's not really a simplicial complex, but okay, sort of.
What do you mean multiply simplistic complex?
Cartesian product.
Cartesian product. It's not really a simplicial complex, it's just whatever. Cell complex, but fine. Anyway, not important. So anyway, it's clear it's less or equal to d, and equal to d is actually a non-trivial theorem. This is not a trivial theorem, this is a deep fact. It's a deep fact, but okay, not a new fact. It's basically equivalent, more or less equivalent to the Brouwer fixed point theorem. You need to input some non-trivial topological inputs to basically show that the dimension of RD is not 0. Or at least not 1, maybe not 0.
But it could be d minus 1. You need to rule out this also, right?
Yeah, so that's what I said. As long as epsilon is strictly less than 1,
Cannot choose
the
it
dimension,
at
you
all.
cannot model it by lower dimensions.
Is there an example where epsilon goes to 0, this goes?
Sure, that's what I want to talk about.
Yeah, but can you say just something more about this? Where is the fixed point theorem come in?
So put a vertex to each one of the faces of the cube. And then, so maybe the easiest is sort of here, at least the way I think about it, easier for me to think about the following sort of similar statement. So you take U to be, here's another, basically the same thing. Here's a theorem. So suppose U is an open cover of Zegnet cube. No open set meets two opposing cases. Okay, that sort of you could see the relation. Then actually there is a point covered at least e plus 1 times. And what you do, I mean, you sort of you fix for each open set some corner of the cube which includes all of the, which meets all of the faces that my open set meets. And then by some partition of unity, I can map, actually take some partition of unity for this open cover. I take any point in the cube and sort of make it some linear combination of the elements of those faces which contain it, and then somehow, if you are if you only are covered d times, and basically you sort of be the image of this map is going to be on some union of d minus 1 dimensional spaces, there will be some point omitted, and then I would somehow use it to project everything to the boundary. And
That's like a Borsuk-Ulam type of thing.
it's, no, Borsuk-Ulam is fancier.
Fancy.
It's more, Borsuk-Ulam should come later, as sort of the fancy tool. This is, I think,
Simpler, okay.
this is simpler than Borsuk-Ulam.
I didn't understand it, but I guess you can.
I think there's a version like of Sperner's lemma, which is equivalent to
Which is
both.
equivalent to Borsuk-Ulam.
No,
No,
Blauer.
Wow.
No, but it
Well-
proves there's.
Sperner is equivalent to Blauer, and I think Sperner gives, at least for the
It's probably, yeah. I mean, it's not,
some variant of this.
Okay.
Is it important to understand for later in the talk or to
Yeah.
it's important, this is important.
It's still-
To accept this is important.
No, that's fine. I'm asking seriously, like, but do I have
I mean, this example was not randomly chosen.
sure.
So now, okay, now we're going to take, now we're going to look at dynamical systems. So now mean dimension. So I'm going to quote two authorities in this talk. One of them is Gromov, one of them is Shannon. Whenever I say that something was introduced by Gromov or Shannon, I don't have any responsibility of explaining why it's important or not. It's Gromov or Shannon. These are the authorities. Gromov comes here from time to time. If you want to ask, you could ask him.
But you were.
So X is now again a compact nice space, metrizable space. And T from X to X is homomorphism. And I'll give an example in a moment, but I don't know. That's not such an esoteric situation. I would be interested in infinite dimensional spaces. So this is dynamical system. This is topological dynamical system. And somehow mostly to actually relate it to electrical engineering, also so appeared in many naturally there's also we also talk about flows. Flows are basically something like, so I have here a space, now I have GT. So I have an R action, let's say GT, going from space X.
That in your list of people you can talk about justification, and then when he was writing at this point, he was calling a flow a dynamical system. You remember? Found it very confusing. The flow meant power.
So one of the interesting things about the talk today is that this talk I'm going to give that actually not about anything that Thorsten did. It's a very unusual.
Kind of,
But Benji will appear. So this is just like a map, just a continuous map. Continuous map from R to X. X sort of write it in a slightly strange way, but okay, fine. This is the way I write it, but it's just a continuous map from R times X to X. And of course, G0 is identity, and GT, GS red, with GT plus X. So
You're missing a G before the. You call it G of TX. It's equal to. There's an equal sign there that just, I think, G on the left side. You're defining the function. You see what one of them is?
For X, the X.
Yeah, either make it an arrow or, yeah, okay, thanks.
You're right. So now if I have a metric D on my space, I can define maybe I'll make a new definition. So now I'm going to define W. X of my space. I'm going to give a metric. I'm going to give an epsilon. I'm going to give an N. Okay, so another parameter. And this is minimal dimension of simplicial complex. Epsilon modeling X according to the metric dn, which is the maximum I from 1 from 0 to n. Distance between t to the x and t to the y. Okay, I mean, there are, if I have a dynamical system, there's two ways I can sort of be more fussy about when points are close. Maybe I want to take them closer, and maybe I just want them to stay close for a long time. I keep this above because I hope I'll reach in less than an hour rate distortions, and we'll sort of after rate distortion we'll take a short break. But we'll see how we go. And now I can define the mean dimension. Okay, so now one thing I want to remark, note that WI dim X D epsilon n plus m is at most WI dim X D epsilon n plus WI dim X D epsilon m. And why is this true? So suppose K1 P from X to some points of some simplex K1 epsilon models metric n, maybe phi 1, phi 2, x to k2 epsilon models dm. So, and obviously, dimension of K1, I take it to be minimal, so it's sort of this WID at the epsilon n and K2, dimension K2, with obvious modifications. Then K1 times K2, and sort of epsilon models dn plus m via the map. I take a point x to, and now I need to take it to a point in this Cartesian product, so I'm taking it to phi1 of x, phi2 e to the n. But then this epsilon models up to time n plus n. And okay, like I said, it's not really a simulation complex. It's a cell complex. I can work with cell complex. In fact, I prefer to work with cell complexes. Okay. And now I can define, so now once I see this kind of subadditivity, I mean, there's something that's itching in my bones. I want to look at the limits as n goes to infinity of this WID b epsilon n and divide by n, which is of course equal to the infimum because of the subadditivity, and then I'm going to take the limits epsilon goes to 0, and this I call, this is the mean dimension. This is first word in my title.
In this definition, where the subadditivity proof epsilon does not change, you use this map?
No, that's the point. Epsilon does not change because I sort of, the whole thing is sort of, yeah, no, that's important. The epsilon is the same epsilon. I mean, this is not an isometry by any means, but if you see what this means, that this thing epsilon m models my point, it means that if x and y are close after I apply times t to the k for k between capital N to capital N plus m, they're going to stay close. That's exactly what I need. But the definitions are set up so that the epsilon is everything set up in the right way.
Because you look at infimum, N infinity, right? And then
yeah, I'm looking at
something.
yeah, I'm looking at this stuff. Yeah.
Like a nice intuition to think about it. If like the space gets squished into something lower dimensional, this would.
I think the best intuition is to give you an example. But just one thing I want to say, this is for systems of, it turns out that it's easy to show that if x gt is a flow, then mean dimension x. So now I'm not taking this as a flow, I'm taking it as I apply this maps that takes the point x to x after t1 times, okay, just one map. So this is exactly this definition. But I could do it for t2, why not? I mean, I could do it for any time. And I just put here t1 over t2. In dimension is positive, so I put absolute value for any t1, t2, is t2 not equal to 0. That sort of turns out to be 2. So now I can talk about, so this common value, so the common value of, so maybe mean dimension x g1, I would say to be the mean dimension of my flow. Example. So if you open a dynamical systems textbook, you look at the examples, whatever, geodesic flow, cat map, whatever. All of them have finite dimension. And obviously, if the dimension of x is finite, then the mean dimension is 0 because whatever, I mean, I can take this resolution of epsilon for n times. If I took the points extremely close to the continuity, they would stay close for n times. So all of these things are bounded. Whatever epsilon n are always bounded by the dimension of the space. Because the dimension of the space, I can model it arbitrarily accurately. And then if I have a fixed number divided by n, I'm going to get 0. So any finite dimensional system has mean dimension 0. And so let's take an infinite dimensional system. What's this simplest infinite dimensional system? I want a compact space. So here's the simplest thing I can think of. But maybe I'll be fancy. Not the simplest, this is just a cube, but to the power of z. And have a map from it. What would be the map? So I take a sigma x. So x is xi, and each xi is inside the cube. Sigma of x at the point I is going to be xi plus 1, the shift. Okay, that's the shift, which you're used to, but the alphabet is unfortunately or fortunately uncountable, and not just uncountable, it has some topology. So I need to define a metric. Yeah, I apologized already, so I won't apologize again, but I'm going to call the metric D. Not so important what I'm going to take, but maybe it is. Okay.
Any reason not to take d in the dimension of the cube to be 1 for this example? It's important it's some larger number.
No, I just no. There's a expositional advantage of taking it to be 1, and there's an expositional advantage of taking it to be d. And I somehow it's just okay. Once it's an expositional thing, it's sort of yeah. You're very welcome to think of just ignore the d here.
Okay, so that's the distance is infinite, right?
Yeah, that's infinite. And now because of this example, so if you look at I try to model my space. So this metric is in particular bigger or equal to x0 minus y0. Okay, so if I look at the dimension that's captured by my metric up to time n, so this basically means at the very least of 2 points, diameter less than epsilon with respect to this dn metric basically means that, totally means that the first capital N digits are close. The image of some, I have some map for my big space to some simplicial complex, so that the inverse image of any point is going to have they would be separated in the L infinity norm by at most epsilon in the first n coordinate. And so what I'm trying to say is that by the exercise above, this is bounded from below by n, because basically n times d, because you're basically this implies so x minus y n less than epsilon implies that xi minus yi infinity less than epsilon I 0. This is dn. This dn I described. This dynamical entropy takes the maximal of the action from times between 0 to n. So I apply my dynamics between 0 and n minus 1 times. Less than epsilon implies that the coordinates between 0 and n minus 1 are within epsilon of another, and is implied by something like that.
Sorry, slow down. Remind again, capital D with
This
N,
is-
what did that mean?
This thing here
Yeah.
is a maximum, the distance between sigma to the kx, sigma to the ky, k between 0 and n.
Without normalizing by N.
No normalize,
Just
it's the
the
maximum.
Okay.
Maximum, it's sort of not natural to normalize. I will normalize later. I mean, that sort of would happen. Going to happen.
And what's written, so if the distance is the infinity here with respect to xi is just
This is this.
the d coordinates?
Yeah, this is so the big A. So every time I put a line under, it's sort of it's a sequence of small
Over
x's.
there, it's just the coordinate itself.
Yeah. So maybe Avi was right. I should have started just with
No, it's
interval, but so anyway, this WI dim is somewhere between E and plus y. Epsilon or something like that. And when I divide by n, I get the in dimension. And now I get to the point why I wanted to somehow.
Sorry, but how do we get this other implication with the log epsilon?
Basically, I mean, if you
Like the tail of this always tends to.
if you sort of have some extra digits, then somehow the effect of all of the. So if x and y are the same between times minus t to t, then the distance between them is at worst 2 to the minus t.
Because
That's the law, because I'm sort of taking exponentially decaying.
Is it log 1 over epsilon or?
Look, absolute value. That's it.
wrong place.
But when epsilon is smaller to do, it get bigger.
Yeah, but log x will be negative, that would absolute value. Right.
It's log 1 over epsilon, yeah.
Yeah. That's good. But it's again something that I'm always, pedagogical question that I'm always, in my classes, I never, like when I define entropy, I always take log 1, you know. But then I thought here maybe people would complain about this. Anyway, maybe log 1 over epsilon is how I think of it. I don't like the absolute value, but okay, whatever. So the mean dimension of this shift to cubes is, so I take whatever upper bound, lower bound, I divide by n, go to the limits, it's exactly d.
So this would stay the same if you instead took not exponential decay but quadratic decay. Epsilon will go to 0. It will not be log 1 over epsilon, but it will maybe be 1 over.
Possibly, but I mean, you could make it. So, mean dimension. So the answer is yes, but mean dimension. Yes, mean dimension is invariant of the topology. You could take any equivalent metric and get the same answer.
Yeah, it's so clear to me that these are equivalent metrics if I do.
Yeah, exactly. It would be equivalent, and so they give the same mean dimension. But as we would see in a minute, we would somehow, there is sort of a reason to, it's not just because of idiosyncrasy that I insisted to talk about metrizable space and not to fix the metric and done. In a minute, the metric will play a role and sort of so like we said, dimension of my space, the mean dimension, now another thing which is less clear, and I will define what this is, but I'm sort of slowly, the rate distortion is the wrong place. I'm slowly approaching rate distortion. Okay, so but I said that Shannon entropy, Shannon will come soon. The topological entropy of S is finite, implies that the mean dimension. This is not obvious. This is something Benji Weiss and I noticed. Topological entropy less than infinity implies that the mean dimension is 0. Let me try to explain why. And maybe before I can explain why, I need to explain what is topological entropy. That would be a good step forward.
The example, you didn't really care about this being cubed, right? You put it like in a product space of any
Okay.
We dimension.
So here is a problem. Any definition of dimension, except in C, doesn't really act nicely in terms of products. So if you look at compact metric spaces and you take the product, the dimension is at most the sum of the dimensions, but it could be smaller.
Yeah.
But you could take here any simplicial complex not just a cube. So in particular, for future reference, I would like you to look at the following example. I call it XY. And why do I call it XY? Because it takes a space Y, and Y is not the letter, but this graph on 4 vertices, 3 edges. Okay, and I can look at this shift. It will also have mean dimension 1. Okay, I mean, take any simplicial complex of dimension D, any nice space. But this particular example will play a role later in this.
Here the metric is a graph method. Here the metric is a graph method.
No, I mean, it's a geometric graph. So the metric is the distance in the blackboard.
Yeah.
This would come into picture when we get to list decoding. Okay, promise to look at another way I can try to model a space up to accuracy epsilon. The sort of combinatorial, I can try to sample it. So I define n x b epsilon is a minimal number of points in epsilon net. So the minimal number of points so that every point is guaranteed to be within epsilon of one of the points in my set. And I can define, again, I'm sorry, like I use d twice, I'm using n twice, but I mean just to be easier. So this is in a dynamical system, minimal number of points in epsilon net with respect to metric. So this with respect to metric D. And now I have some dynamical system with respect to metric Dn, which is the maximum I from 0 to n, distance I have y. Okay. And then again, similar kind of subadditivity. If I have an epsilon net up to time n and an epsilon net up to time m, then if I take the product, but okay, I need to shift by t to the n in the right way, I can get that the product of the nets shifted by the right applying application of t is going to be an epsilon net for a longer time. So and okay. Once I see this, I'm almost as excited as when I see subadditive function. I just take the logarithm that I'm as excited as I have when I see a subadditive function. So I'm looking at it's the epsilon is going to be the limit 1 over n log beginning to be it's epsilon m, and then topological entropy of my space is just a limit that epsilon goes to 0 of this. Okay, so this is topological entropy, and we're running a bit out of time, so I'm not going to explain too much, but sort of a hint why entropy. But this is really a hint. So you fix epsilon. And the simplicial model. Epsilon model phi from X to some simplicial complex scale. And then, obviously, if I take the Cartesian product of K n times, is going to an epsilon model in the sense that I can, with respect to this metric, that's the maximum. Now, okay, so this is in particular, right, a continuous map. So I get here a continuous map, phi n from x to k to the power n, which, okay. Realize this epsilon modeling. And now take eta wave, eta tiny. And I can cover my space by and large. Cover by something like eta to the minus, not eta, to 2 to the h entropy plus epsilon times n for n large many eta balls. N eta balls. And now an n eta ball under this map, because it sort of only looks at n times, it's going to map into tiny balls here. Okay? So the image of X would only be contained in a relatively few number of tiny balls here. And then what happens is that any simplex here, which I have a point inside, which is omitted by the image of X, I can pop this simplex. I can project everything to the edges of the simplex from this point that does not exist. And because I have so few points, I can basically pop simplexes up to pretty low dimension. Okay, that's sort of the idea. Oh. I think of simplexes as simplexes that has a point not in the image. If someone asks me if I'm assuming that the model is surjective, I'm not assuming, and I'm exactly using points which are not to pop to simplify my model.
So if n sub ball is n times a sub ball, what is the n sub ball?
And a ball is a sort of ball with respect to the Dn metric. Epsilon ball with respect to Dn metric. Yeah, which is just, it's not really a product, but it's sort of shifted in time. Okay. So now,
To be clear, there was a proof that's on the left, yeah. That's outlining a proof of this.
so this is the proof of this. And in fact, if you quantify it, you would see that the topological entropy is bounded from above by the limit epsilon goes to 0. Maybe, and then I'm going to take here the I'm looking at, so if I just take this thing as the epsilon I wrote above, if I just take the limit, I get the entropy, but actually I can I'll divide by log of 1 over epsilon. Now it's no longer guaranteed to exist. I mean, this may increase or decrease. So the lim nth of this thing is bound from above for topological entropy. Okay, and this is highly dependent on the metric. So if I take the cube with the metric that I erased here that I defined, with this exponentially decaying, you would see that this thing here would actually converge to the mean dimension. Sorry. At the mean dimension, it's meaningful for systems with infinite entropy. So it basically gives you an lower bound, whatever metric you use, on the complexity at scale epsilon divided by log of epsilon. Okay? It sort of gives you something for, if you use the metric that I gave you, the nice metric that I gave you for the Hilbert cube, you would actually get equality. If you use a metric where you decay by n squared or something, you're going to get a bigger value for the right hand side.
It's a better bound of the mean.
You would get a worse bound if you use the wrong metric. It's like in house. So now I'm going slowly to ray distortion. Now, Elon was very worried about more or less everything I put in my title and abstract, except one thing Elon was happy with, Shannon entropy. So let's try to relate this to Shannon entropy. So it's not quite Shannon entropy, but Kolmogorov-Sinai entropy, but basically, so basically you can define the Kolmogorov-Sinai entropy. So now, but Shannon entropy is about a stochastic process. Shannon entropy is a stochastic process. How do I get stochastic process? Maybe finite states. Even though you can make it countable states, could do another thing, but the finite state stochastic process. How do I take my system? I have a compact metric space X and T, and how do I make it into a stochastic process, finite state stochastic mode? So I'm basically need to add two things. So I add mu, a measure, probability measure, which is G invariant. Right, the push forward mu is equal to mu. And I need to add some partition of X. So usually when I say a partition, I take a collection of subsets, but because I want to emphasize the processy structure, I'm actually thinking of it as a function for my space to find it. And then if I have this For tuple, I can define the entropy as Shannon entropy. I can define the Shannon entropy. Is the limit of the entropy of the random variable, according, of course, to this probability measure mu, of the random variable px, px, p to the n minus 1x. Right, entropy of random variables, this is the one thing that I was allowed to use, divided by n. And the great insight of Kolmogorov, some sort of Kolmogorov-Sinai entropy, is that if you take the supremum overall partitions, you actually get something which is invariant of the dynamical system, sort of have some number which is meaningful for the dynamical system. You could calculate that. And you get the entropy of a space and an invariant measure.
M is fixed here or M is also goes to infinity? The number of parts. The number of parts.
No, the partition P is fixed.
Yeah, it's fixed.
Here I take the supremum, so maybe you take bigger and bigger partitions. But in practice, so it's a theorem that if the entropy is finite, you can take P to be at most 2 to the entropy.
This is like the alphabet, what is that?
Yeah.
Yeah.
What's the great insight of Kolmogorov?
That these things that the information theorists were talking about, they're actually relevant to algorithmic theory. But I mean, if you have a geodesic flow, right, a geodesic flow, I mean, there's no obvious partition to take, so why? But so it's like the supermoon, sort of beautifully behaving variance.
You should say, great theorems which classify a dynamical system by the entropy in special cases.
Yeah. So those sort of, Ornstein, and yeah. Yeah, but I mean, I have a very ambitious goal of going through all of the world, and I've reached so far. I'm around. I got halfway to the definition of rate, toward the definition of rate distortion. Okay, and there's a beautiful theorem, variational principle. Beautiful theorem which says that the topological entropy of a dynamical system is the supremum of the Kolmogorov-Sinai entropy of the dynamical system. Maybe I should put your T, I don't know. Overall measures mu, which are T invariant. Okay, it's a beautiful statement. It's again a big question. When is a supremum achieved? Can you find a measure of maximal entropy that actually realizes? Can you find a stochastic process on my space that actually realizes this sort of beautiful theorem?
Elon showed this.
I forgot the name, but that's sort of.
I think in the West, well, there was a lot of.
Lewis. Our
Not Lewis.
No.
Rufus.
But I don't
And it was not in Russia, I'm sure.
Actually, no, it's less well-known people, I think, in the West. Actually,
Maybe even in like time, like 70s, 80s, when was like
Yeah, 70, 60s, maybe 60, 70, something like that.
I mean, I think Adler defined topology.
Adler was actually involved. Adler was certainly one of the people. Roy Adler was one of the people.
So how typical is the measure is unique? I mean, for the
Unique, that's a complicated thing, but at least that there is a measure of maximal entropy. If you have a finite dimensional dynamical system and the map is C is infinity, it's true. But if it's Tn for finite n, however large, it's not necessarily true.
Yes. Not only the maximum entropy one, just an invariant measure. And always.
Oh, invariant measure is unique, is very atypical. Very atypical. That's very atypical. But since you mentioned it, so a system is uniquely ergodic. Uniquely ergodic if there exists a unique T-invariant measure. And okay, it's very rare, but any abstract measure preserving system you could realize as a unique invariant measure of a topological dynamical system. So it's rare, but not. And another non-obvious thing again, this is something that Benji and I showed. Then the mean dimension is this. That's not. Okay. So now let's talk about the distortion. And this, so when Shannon invented information theory, that was before the digital revolution. So he was worried about analog transmissions, probably more than he was worried about digital transmissions. So he was wondering, and sort of, you could think of, you have some voice recording, you wonder how much information, how many bits do you need per second to encode this voice. I have a recording of some classical music. I want to compress this. How much bits of information do I need per minute of the concert? So he defines, so he has, so Shannon's rate distortion. So Shannon had a space, compact metric space, he had a transformation, he had some notion of distance, and he had an invariant measure, okay? This is what Shannon was using, and he was trying to see how much information context this has. And of course, the short answer is that the entropy would be infinite, because sort of if you want, you have infinitely many bits to, but here's how he defined it. So you mutual information between two random variables. So we talked about entropy of random variables. Mutual information between two random variables is if x and y have only finitely many values. You define it to be the entropy of x plus the entropy of y minus the entropy of x and y. So it's the amount of information shared between x and y. And if x and y are not, don't have finitely many values, you take the supremum of all partitions of x and y and you define it also. Of course, if x and y have infinitely many values, this may well be infinite. still can be defined in a meaningful way. And it could, even if X and Y have equal entropy, this could be a well-defined finite number. So now, I'll define rate distortion, then we'll take a 5 minutes break and then we'll continue. So, a probabilistic and epsilon model of this X T mu B is a probability space and random variables, X values, little x, y1, y, maybe y0, yn minus 1, such that x is distributed according to the random probability mu, and the sum, and basically these yi's are epsilon close to x. This time I'm not taking supremum norm. I'm taking the average norm. You could have taken supremum norm, but Shannon took the average norm, and like I said, with Shannon and Goromov, I'm not arguing. So I want to epsilon model. So the yi's, but they don't come from, they're just, this is some discrete space, and the y's are not any orbit of anything. And okay, then you take the rate distortion, T of mu epsilon n is the infimum of the mutual entropy between x and y 0, y n minus 1, when x, y 0, y n minus 1 is an n epsilon model of x. Okay, so this basically measures how much information I have in my process up to, if I care about this metric dn, or maybe not this metric dn, but this sort of Hamming average method.
Well, how do we think of the yi's? What does it mean that they appear as the model? Until now, model was a simplicial complex.
Yeah, so now
any random variables in it.
No, so I had one model with a simplicial complex, another model with a finite set of an epsilon net. Now it's another model with a simplicial. So here's an example. Maybe I take my favorite system, metric. Favorite metric. Measure, what measure would I take? Is just Lebesgue over each component IID. Okay? And then I think one good thing to take is I could take yi to be the epsilon truncation of the digits. So we're going to take x randomly, and we're going to take yi to be actually a function. So yi would actually be a function of x, it would be the epsilon truncation of xi. And then this mutual information would be basically
xi is tix.
xi is sigma to the IX zeros component, right? So that's how it fits into this big picture. And then this information, at least this RMU, that's sort of an upper bound. It's one model, but it's basically it's easy to see that it's basically something like log 1 over epsilon times n, or something like that. Okay, and now, okay, since I got questions and I got carried away, I mean, the break, how am I allowed to go a bit over time if I give a break?
Definitely are allowed to go over time.
Okay, that's good. So then
It's also
I,
good to have a break.
yeah, the break will be, but then it'll be a bit over time. But now here's a theorem of Tsukamoto and myself. Now, for any the mean dimension x is at most the limit 0. And okay, I mean, again, somehow the limit, because of the subadditivity, is the limit of R mu v mu epsilon n over n, as n goes to infinity exists. That sort of follows from the nice definition of Shannon. So this is at most the lim inf of the limit n goes to infinity of the rate for supermoon. Over the measure mu of the limit as epsilon goes to 0, limit n goes to infinity for R epsilon d mu over log 1 over epsilon. And
Obviously, we're supposed to compare this thing on the left, yeah.
Yeah. What's the relationship
You
between?
brought on the left your previous theorem with Benji, and this, you're going to explain upper bound for mean dimension.
so this is the mean dimension. This is
Now look left,
Left.
left in the bottom.
okay, yeah, that's a good question. So this number is going to be smaller than this number. But I didn't say, and if my system is nice, has a watch, or can simulate time, and okay, we'll talk what it means after the break. Then actually, you could actually say the mean dimension of xt is the infimum overall matrix D, supermum overall invariant measure mu of this limit, and you could actually, it's actually not infimum, it's minimum. You could actually find you can find a metric for which here it's a supermum, the limit epsilon goes to 0, and you can put here lim sup, lim inf. I don't say the limit exists, but I say I don't really care if you put lim inf or lim sup, whichever way you want to do it. So this is a double variational principle. You take, it's sort of a min-max thing. You take metric that minimizes, measures that maximizes, and this expression. This is actually going to be the mean dimension. So the rate distortion, so Shannon's rate distortion is very closely connected to mean dimension. So, okay. So we got here I didn't go this would be for the next half hour or so that I would get after the book. So when you wake up in the morning, the most important feature of an alarm clock is the snooze function. Okay? You press a button and you are guaranteed to have some time until the next time it snoozes, and there's an upper bound when you hear this. And it's not so important if it's exactly 5 minutes or 6 minutes, but just you want some time to continue sleeping, and you want to know that at some point it would wake you up. And I want the same thing for my dynamical systems. So I need to explain this as a clock. So the accepted name, it's not a bad name. Time marking property may be even better if for every n there is an open set. U and n such that
Here's the next.
Hmm?
Here's the next.
an integer u equals to the joint with the union I mean, because the space is compact, I could just put here, ignore this capital N and put here up to infinity. Same things. And okay, there are many systems that have this. Any minimal system. Example. Any infinite minimal system.
Just the name marker, that's what's written there?
Yeah. The simplest, the nicest, okay. The dyadic numbers and X plus one, an odometer. Right, like odometer of a car, only base 2, but you could take base 10 if you want. And infinitely many digits because these cars run a long time. And one way to get a system with a watch, if it doesn't have, for instance, the shift on intervals doesn't have a watch, you can't do this. You could show that. One way to do that is to just give your system a watch. What does it mean to give your system a watch? So if X is a dynamical system, and YS is one with a watch, has marker property. Then X times Y, T times this, and no. It's related to a real life thing. I mean, you have sort of transmission and you want to be able to synchronize between the receiver and the transmitter without passing additional information, right? Sort of. But anyway, this is what it is.
Yeah, why is this the right
Hmm?
definition for keeping time?
This is I press my button, so I wait. So this means that if U is in X, then if X is in U, then TX is not inside U. So I sort of snooze until for a little n times, then I'm guaranteed that I will be woken up after at most capital N times. Okay. So bandwidth. Next word.
So you said that the shifting operator on R is not a good, doesn't have this marker property.
What I said is that this does not have this marker.
And now you want to.
I mean, one thing the Markov property guarantees. So the Markov property is not completely harmless. It guarantees that the system has no periodic points. Because the periodic point of period less than capital N, I mean, either miss this set U entirely, or would hit it with probability with at least the frequency of the period. Okay, so that's a good point. A Markov property implies that you have no periodic points. So you sort of, by multiplying it by a system with a Markov property, you sort of just open up the periodical point. That's sort of what happens. Bandwidth. So again, we're talking about Shannon. So the Shannon-Nyquist theorem, right? Shannon says that about sampling, but here I'm going to be a bit deviate from the classics. Okay, it's not natural from my point of view to talk about the L2 signal. I mean, I get whatever new transmitting equipment, it isn't bounded by the L2 norm of what it can transmit. It's not the natural estimate in the real world, and okay, certainly for me, is L infinity bound. So I'm going to look at the space. I think this is the standard definition of it. Bernstein space. These are functions f from R to R or C, not so important, which are bounded, continuous. And the support of the Fourier transform is contained in the minus or maybe a half. So the width of the band is A. My notation of the Fourier transform of a function f of a function is integral e to the 2 pi I Cx, maybe minus f of dx. And of course, this whole thing is meaningless. I'm looking at the bounded functions. There's no reason to converge. I need to make sense of it. And instead of making sense of it, I'm going to define it in a different way, which is equivalent. You could mention it's sort of in the sense of distribution, whatever. But instead, I'm actually going to make an alternative definition. So f is going to be from R to R, such that it extends to a entire function in with the norm absolute value of f of z at most some a times e to the no, this is not a is a reserved letter. Constant depends on f, some kind exponential of imaginary part of z. Maybe pi imaginary part of z to get everything right. Okay. So an example.
Do you care about pi? Can't you put it in the CF to the pi?
No, but I could put it in the A, but then I could put pi in the A, but then example is sine pi of x. Okay, that's a nice example. Satisfies everything. Constant CF is 1/2. Well, not 1/2, it's 1 maybe because anyway, the constant certainly, and notice that this function is 0 at the integers. So now that's sort of why I mentioned Shannon. So I'm going to have my system. So here I'm going to define a new dynamical system. I'm going to define a flow. F is Bernstein space. I had actually, I forgot, I had a nice, I hesitated what, order space, and I had a nice thought, yeah. Signal space, eh? No, this is the space of functions, and there is a natural flow on the space of function. So I have this signal of f. Yeah. It's just f of 6. This is the flow. And there is an obvious metric you would like to use in this space. Not metric, obvious topology, not obvious metric, that sort of. The proposition is that the mean dimension of sigma t is exactly backwards. And so basically, so that it's a flow, so I need to show, so let B, suppose B, basically what I want to show is that if B, or at least in one direction, I want to show you, explain why. So let's prove. Look, the very hand wavy, but y less than or equal to. So take b less than 1 over a. And basically what I want to show is that the mean dimension sigma a will shift by b now, so the fixed b, right? I'm sorry, I'm using, so maybe I should put here a big dot, because I'm sort of, this is the flow. I want to show this is at most 1. And basically, I can tell you what the n epsilon model will be. So an n epsilon model, basically just sample. I'm going to take f would map to f times a b, where k is between minus L and L plus L for L large enough. And L only depends on L depends on epsilon. And basically how far A is from one or more. So that's it. And the point is that somehow by Jensen's formula, this wonderful formula that's for an entire function, relates the absolute value of a function on a big ball, the value at the middle, and where the zeros lie. So if I have a function, if I have two functions which agree in all of these times, the difference would have zeros at all of these times. This can, and I know I control the L, I control the absolute value of the circle by my assumptions that I am in this, by this assumption. And you could show that basically in a big enough circle, I would control the value. If you really have so many zeros in a big enough circle, then your point has to be, your value has to be very small at, let's say, 0. So you could get from Jensen's formula, you can get that f of 0 is less than epsilon if f is at most c x in z times pi times a, something like that, and absolute value maybe, and f kb is equal to 0 for k at most, or something like that. And yeah, so this n will depend on the value of the c, but you could do something like that. That's just Jensen's formula. And then basically you take k between minus L and n plus L, then I control the value of f at times between, I control the size of f on a big interval. So that's just Nyquist sampling revisited. Not in L2 context, but the Bernstein space context, but it's the same. And if you want to go the other direction, it's basically closely related to the fact that you could basically set arbitrarily the other on the opposite side. if D is bigger than 1 over 8, you can find for any x in infinity in F in its Bernstein space, F KB is equal to X. Okay, for F. And you basically take F to be summation think of F of X, think X minus T minus K. XK, X in Z. This thing is sine X over X. But, and maybe here I'm assuming D is equal to 1 or something. But this again has minor problems. This doesn't have to converge. So you actually need, unlike L2 theory, you actually need strict inequality. You sort of maybe think X minus K or delta X minus K. That's sort of complete proof. And then from that sort of, because you could set parameters arbitrarily, and then you could sort of couple it with this very first lemma I wrote about Wi dimension of a cube. This sort of implies that the mean dimension is at least, this gives this result gives you the opposite inequality. So this is really inequality, and it's sort of not the fanciest thing you need to use is the fanciest thing you need to use is the Elf's form.
Use the Markov property or not?
No Markov property. So what I proved, right? That's a great question, because exactly the next line I wanted to say. We proved that if the bandwidth is bigger than 1, we can embed, or let's say bigger than, I claim as we proved that the bandwidth is bigger than D, we can embed this standard system that we had in this bandwidth channel, such that what do I mean by embed? So it's injective. This map is injective, and I of sigma to X is sigma 1. So the action is compatible.
Embedding.
The embedding.
Embedding, so you're.
You're right, I is not the best letter to use. I was planning to use iota, but with this font I have on my blackboard, it's not.
Use DOM.
Yeah. Anyway. So now, I wanted me to give my watch to the system, to the theorem, is the theorem of Gutmann and Tsukamoto. Strengthening a theorem of mine. If the dimension of the system is less than A over 2, if the bandwidth is more than twice as big as the obvious. So this implies, I would say, also such an embedding, the property of mean dimension implies the mean dimension of, you can embed a system in a general, if I have a general dynamic, so let me say this in full important point for any xt. If there is existent embedding psi xt inside shift, then mean dimension xt has to be at least the bandwidth, at most the bandwidth. The bandwidth has to be at least big enough to accommodate the mean dimension. If I have some kind of satellite, it measures whatever intensity of 14 solar flares. I want to see how much bandwidth I need to transmit this measurement. And the only condition I have is that I want my transmission to be continuous. I don't want to do what one does in practice, analog to digital conversion, some kind of manipulation over bits, and then digital to analog conversion and transmitted. That sort of always will introduce some errors. I don't want to do that. I want some continuous thing. Then I'm guaranteed that I need a bandwidth of at least mean dimension. And probably this rate distortion connection also gives the limits, even if you're allowing this digital to analog conversion and analog to digital conversion, if you have some reasonable assumptions. But if the mean dimension is less than A over 2, then you can embed the system in a signal with a bandwidth, say, twice the lower. And 2 is sharp. So take the system shift on this geometric realization of y and equip it with a watch. I mean, this is obviously this is many periodic points, this is not a system of this class. I should, and if xt has a Markov property, if xt doesn't have a Markov property, then maybe just take the map which takes the square. You take x to be the square, and you take the map that takes the point to itself. This has mean dimension 0, but if A is less than 2 or something, you cannot embed it. Because I mean, there are so many. I'm saying that you need to make some assumptions to avoid trivial counterexamples. And you need to make stronger assumptions to avoid less trivial recent counterexamples. But if my system has a Markov property, that sort of means then you sort of can hope that you could have a nice theorem. And if the mean dimension is half the bandwidth, you could encode the system. And the 2 is sharp. you take this system. Now, okay, for trivial reasons, let's say you cannot embed it in the shift on intervals, just because here the fixed points look like a Y and you can't map a Y to an interval more or less, or something like that.
What do you mean that the fixed points look like a Y?
You look in this complicated space, you look at all points X, so that sigma of X is equal to X. It's just one copy of Y.
Constant functions, I think, right?
The constant function is just the constant sequence. It's just one copy of Y. And it's okay. Anyway, equip it with a watch. So take a product. Take a product of this with very simple minimal system, like the Yadi counter, cannot be embedded. In sigma A for all A less than. And here you need to use both equal. Which is basically okay. Homotopy theory in the sky, V2 homotopy theory in the sky.
So what is the satellite transmitting exactly? Just the starting point X and shift? What is the music?
So maybe the satellite has 7 detectors. Every second, let's say, it measures 7 numbers, and you want to transmit them to Earth.
So there is no particular T. There's X, I see, but what is there?
I mean, you do it every time.
So this is just a shift.
Yeah, just a shift. But there is a sort of, I mean, it's not. There is some physical constraints that maybe I'm measuring.
Yeah.
So the data is complicated.
Yeah.
And maybe you could save some bandwidth if you knew something about the data. Okay. So
Again, in this game, you will wait for n measurements and only then direction. You do it in block. The way you
and in order to be able to communicate with blocks, I need to be able to decide when a block begins, and that's why I need the marker property. That's exactly why I need the marker property. Right. So I can, because I want to work with the mean dimension information about blocks, and I somehow have to take some continuous transmission, break it into blocks. And if I don't know how to break it into blocks, I'm not sure how to work. That's exactly a mathematical description why why this marker property is needed. So now I think let's see what we covered. And what we covered. I will cover this because we haven't covered. So this is the sort of maybe the most recent theorem. This is a beautiful theorem of Michael Levin from maybe 24, maybe 23. I'm not good with stats, but let's say 24, maybe 25. If mean dimension, let's call it D, is less than A, then we can find a finite to a map right? for my space to sigma A, intertwining with action, psi of P is shift psi of X. It's a slightly non-trivial question what finite to one maps do to mean dimension. It's pretty obvious that it's fixed. It doesn't change mean dimension, but not completely trivial to prove it. Because this beautiful theorem I haven't heard of in my ignorance before Michael will prove this, that if you have in ordinary dimensions, if you have a k-dimensional space and you have an L to 1 map of it to something, so the dimension of the image is at most, what did I say, k? K plus L minus 1 dimensional.
You have an L to 1 map from the space to another.
An L to 1 map can increase dimension by exactly L minus 1. So the piano curve, you could, you could make a piano curve that's sort of 2 to 1 or increase the dimension. Anyway, so this is some kind of, so it's not completely obvious how mean dimension works under finite to one maps. It certainly cannot decrease mean dimension, probably cannot increase mean dimension, but I'm not completely sure.
So the finite depends on the how close.
Okay, with cardinality of a point. So basically bounded by 1 plus some constant over A minus squared. You could expect it to be A minus D, but the proof gives A minus D squared. Okay, so this is just analog list decoding. That's what it is. And you will realize here, so realize here something which I'm sure has been seen in this seminar many times, that you have some kind of stupid entropy theoretical bound to coding, and you can't reach it, probably can't reach it. But if you are willing not to use coding, but list decoding, you could get to the limit. And okay.
Why is the factor of 2 necessary? I mean, the factor of 2 in list decoding in the discrete case come from binary alphabet. Here we are in a continuous alphabet.
Wonderful question. Basically, by this analog to digital conversion up to some small thing, I can think of this bandwidth limited function as, so I told you that I can recover the signal if I sample with frequency bigger than 1 over the bandwidth, and I can construct anything if I tell you what happens with frequency less than 1 over the bandwidth. Morally, basically a bandwidth signal is basically the same thing as fixing at exactly the bandwidth, the value. So basically it's like the shift on, if I change the time to be, if I move by 1 over the bandwidth, and basically the system is essentially a shift on intervals. Now, the theorem that if dimension x, then x can be embedded in d plus 1 and this is that. But that's well known. D-dimensional space.
Which dimension are you using?
Simplicial complex.
Okay, and then it can be embedded in.
A graph, you could always embed in 3 space, but you could not every graph is planar.
Well, embedding is what you want to maintain.
You don't embed, maintain just topologically embed. That's sort of something you do. That's well known. And so now the example is you take a skeleton of whatever 2k plus 1 simplex or something, right? This is what you do. And that's not so good for me, but using this Bourse column, you could show that if you take. So this is the planar graph, this Y. Can be embedded in 2 dimensions. But this cannot be embedded in R 2D minus 1. This is the goal. And then this is why somehow for the shift on Y, it's okay, I had to work because I wanted to be able to avoid. You need at least twice the bandwidth. And it's, I mean, how does this come about, this tool? It's exactly your tool. How does it come about? It basically comes because if you have you have some kind of simplex here, you randomly put points in Rn, and you want somehow 2 simplexes that are different not to intersect, so you need exactly 2D to be smaller than n, so that typically they won't intersect. It's exactly the same reason for your tool. Sort of what is possibly interesting is that the fact that there is some topology that's trying to explain why without list decoding you have to go use bigger bandwidths.
You think there may be a more direct connection and where you can infer a theorem in the discrete form a continuous or vice versa. I mean, is it
possibly? I mean, things are very parallel somehow, right?
I know, yeah, but since they are similar statements.
Yeah, so I would wonder if you could somehow maybe. Yeah, so one thing you sort of wonder whether you could. I don't know if there are interesting cases where you have empirically this gap of needing twice the number of bits to encode something without a possible proof that you can't do better. But if there are interesting settings where you have something like that, then possibly you could sort of, maybe this kind of topological ideas could be relevant. I'm not sure.
It's usually more packing arguments, the cello arguments.
Yeah, I don't know.
I mean, the Bourse column is not just a packing.
No, it's not.
Anyway, the parallel is clear somehow.
Okay, so third one. Any comments or questions?
Could you remind me of the approximation used for space sigma A, like when we approximated functions by some, function with some
Yeah, I mean, how did I get a simplicial complex to approximate it?
Sorry?
How did I get a simplicial complex to approximate it?
I think I'm talking about the part where you're just had a bunch of points and you wanted
Yeah,
to
that
talk about
was the same part.
Okay.
So, right, I mean, mean dimension, I was saying what would be the minimal dimension of a simplicial complex that I can use to model my space. A simplicial complex I used, well, not a simplicial complex, of course, because I'm cheating. It was a cube, but it was a right dimensional cube, and the map was not a very surprising map. It was just sampling in a discrete set of terms.
Sure. And then how were you, what was the argument that like interpolated on other points?
If you have a function and you have a bound, so Jensen's formula basically gives me, I know a bound on the function in terms of the imaginary parts of my complex number, and then Jensen's formula tells me that the integral of the log of the absolute value of the function on a big sphere is basically equal to the log of the value at 0 of my function plus something involving the zeros. And if I had, so I wanted the inverse image of any 2 points in my model to have small diameter. So if there are 2 points, 2 elements in my sigma A, which under this model map to the same point, it means that they have a 0 at all of these sampling times. So I have some many zeros. Maybe this would be more zeros, but this would just give me even better bound on the side. And that's the usual thing that the file analytic, that the entire function with many zeros wants to be small. So it's the usual Jensen formula, which one uses one of the few things I know how to use about complex analysis.
Thanks.
Any more questions? All right, so thank you again.